Hello classmates, Tim Outland, final assignment, week 8 persuasive speech. This is a follow-up from my week 6 information speech on solar power. I will be presenting this in an attempt to challenge the precept that solar power is a zero-emission salvation of the planet and the solution to the global warming climate change issue. For my references, I use lowtechmagazine.com, stanforduniversity.com, yaleuniversity.edu, extremetech.com, and my own personal experience gained in building and maintaining my own off-grid solar power system I installed in 1998 at my hunting camp. Whenever I hear someone opine about the exemplary energy that solar power is, and offering that we need to get rid of fossil fuel power plants now because they're hurting the planet, I ask, what do you know about solar power? Few that I ask have any real experience, or say, well, you put panels on the roof, they capture the sun rays, and then they make electricity. This is partially correct, and I attempt to explain the rest of the story. While I am not an expert, I do have first-hand experience and knowledge of solar power, as I stated while citing my references earlier. My next question is, do you know where solar panels come from? Generally another pause, followed by a no. As you might surmise, solar panels do not emerge from the ground on their own. They're fabricated from materials extracted from Earth. Materials that are mined, smelted, processed into raw aluminum, copper, silica, glass, and plastics for use as a solar panel. All of those operations require significant fossil fuel and electrical energy to support manufacture. It takes energy to make energy. Fossil fuels burn to generate electricity, or even extraction, capture, and storage from the sun. Some methods are more efficient than others, but there will always be a deficit in the process. With regard to solar energy panels themselves, the following abbreviated material shopping list shows how much energy is required even before that first watt of solar power is generated. Reclaimed aluminum requires 3,100 to 4,700 watt-hours of electricity to be turned to raw aluminum. If you remember from week 6 speech, that is 1/3 to 1/2 of the total electricity produced from the typical household with a 12 by 12 solar array. This is the energy required to return to 1 kilogram or 2.2 pounds of recycled aluminum. 17,000 to 31,000 watt-hours are required to make 2 pounds of plastic. 16,000 to 34,000 watt-hours for 2 pounds of copper. 63,000 to 95,000 watt-hours for 2 pounds of virgin aluminum, and a whopping 2.1 million watt-hours to make 2 pounds of electronic-grade silica products. Add in the expense to transport complete and raw solar panels, the carbon footprint becomes significant, a detail often lost in any green energy discussion. As in any manufacturing process, hazardous waste materials are generated. For example, if you know of a nitrogen trifluoride, or NF3, it's a greenhouse gas associated with high technology devices, estimated to be 17,000 times more impactful than CO2. Computers, flat screens, and solar panels, to name a few, are NF3 users. There is also another unknown. What is the impact for the future for disposal of solar equipment in use today that will have to be retired and replaced later? The electricity produced by solar panels is DC versus AC energy, so it must be converted to be able to feed the appetites of AC powered devices of our modern world. Every time there is a power conversion, there is also an energy loss, which either has to be made up with more arrays or tolerated as an allowable inefficiency. Converters to change DC to AC are another manufactured piece of equipment drawing on the Earth's resources and having an impact to the carbon footprint of clean solar energy. Since the Earth evolves around the sun and on an axis, it is not available 24/7. There are periods of darkness, low light, where solar power production is compromised. For those times, you will now have to include as part of your solar power strategy storage devices, batteries, or other emerging storage technologies to have adequate power reserve for those times when the sun is not around or is weak. Again, more conversion losses and infrastructure to make stored energy available in quantity to keep the lights on. Wire and cable are also required to get the captured power from the solar panel to the batteries to the inverters or both. And finally out to where the electrical need is, another step of a carbon footprint. Solar technology also brings with it a much more perishable life than conventional power methods. At current, the best solar panels are 20 to 25% efficient when new. During their 20 to 25 year life cycle, they lose 1 to 2% efficiency year over year. They aren't overhauled during their service life and have to be replaced with new when expended. For storage, the service life of the best batteries today are 5 to 7 years on average. Have to be replaced again, more impact, and also comes with a possible recycle, hazmat, or landfill issues. The physical real estate required for a farm of panels is significant. It takes approximately 1 acre of panels to produce 1.5 megawatts of electricity, challenging our available land resources for a power generation method that is only effective in making electricity for just part of the day. Allow also that not all areas of the globe have adequate sun days for maximum year-round production of sun-generated power. This is a short list of negatives, often left out of discussion of solar, but the time for this presentation is limited, so I'll end with these for now. Given these negatives, I would like to add, I'm not against solar. As I said in the introduction, I own it and use it myself. We can and should invest in better technology. Alternatives make a lot of sense. They are still coming into their own as a viable option, but are currently incapable of producing serious power as compared to conventional methods, so we need to be smart how we include them into the mix. Today we can and do put on a single 50-foot trailer a 5 megawatt generator set running on natural gas, capable of 24/7 output, 90% or greater availability, 40 to 50% efficiency, with a very low emission output, some even close to zero. The conventional 5 megawatt generator set has a better bang for the buck when compared to solar that requires 5 acres of land for the same output as a generating trailer. The solar array struggles in its own right with a significantly lower availability and has a less desired carbon footprint when all in aggregate is considered. My thoughts to a balanced solution is to improve existing technologies, including nuclear. Yes, often unspoken, energy that does have a place in power generation, versus outright dismantling of existing technology. I'm from an era in the 70s where as a student we were warned by a scientific expert of our impending doom and global cooling due to ozone depletion caused by use of CFC propellants and products. The cure then was to shift to CO2 propellants. Yet it has since been surmised many years later that that hole in the ozone layer probably wasn't so much caused by what we as man do, but a natural occurrence on its own. Now in the 2000s and plus, scientific experts now debate, maybe 50-50 split, what we really have is global warming. And as it turns out, that same CO2 that we had good for the planet in the 70s is bad now. Which is correct? Science and humanity are fickle things. As we learn from exploring our own unknowns, so shall we grow. At one time, it was a 100% scientific fact. The Earth was flat. The sun revolved around the Earth. Man would never fly. the moon was made of cheese, and that we would never be able to make it to the moon to prove otherwise. Possibly I persuaded you, and possibly didn't. I hope at least I left you with a desire to challenge simple solutions offered as finite answers, especially when there's so many other factors to be considered, and in our quest for finding an effective balance without maybe not 100% best solution, possibly a solution with the best compromise until something better comes along. Thank you very much.